So my name is Claire Brown, and I'm an Associate Professor in the Department of Physiology and the Director of the Advanced Bioimaging Facility at McGill University. And today I'm going to talk to you about matching objective lenses to experimental needs and budgets. So just a brief outline. I'm going to start with labeling and terminology. Each objective lens has a lot of information on it that is important to know what that labeling and terminology means. And then after we go through some of the features of the objective lens, we'll talk about what's most important for your application. So is it resolution in XY, sensitivity and speed, resolution in Z, are you doing multicolor imaging? And then we'll round up at the end with a little bit of information about specialized objective lenses. So each objective has a lot of information on it, and it really is the most important component of the microscope. So it's important to know the properties of the lens you're using and make sure it's the right lens for the application. So some of the labeling is quite obvious, the manufacturer, the magnification, and so on. And then other terms need a bit more explanation, such as the working distance and whether a lens is flat field corrected and so on. So this slide can serve as a reference for what the different labels mean and the units that they're in. And there's also a web link where you can see more information on microscope objectives. So what I'll do now is go through these different types of labeling and what they mean. So each lens has two color bands on it. One color band is near the tip of the lens is the immersion color code. So for instance, for an oil immersion lens, there'll be a black band at the front of the lens. For a water lens, it would be white. And for the magnification color code, there's many different colors depending on the magnification. And so for instance, 10x is yellow, 20x is green. And I always make a little joke about, I don't know what happened when we got to 25x, but everything turned into shades of blue. So I don't know if they ran out of colors, or I often think that originally the microscopes were mostly using the lower magnification lenses, so the more diverse colors are there. But from 25 to 63 are different shades of blue. The working distance is another property of the lens, and this is the distance from the front lens element to the surface of the cover slip when the specimen is in focus. So when you put your sample on the microscope and focus on it, it's this distance here between the front of the lens and the top of the cover slip. And in general, this number decreases with magnification. So as you go from 10x to 40x, you can see the lens needs to be closer to the cover slip for the sample to be in focus. And on the lens, you'll see usually WD and a number, and that number is the working distance in millimeters. The depth of field is another property of the lens. It's not typically indicated on the lens, but you can find it on the manufacturer specification sheets. And I think it's best seen here in this image from Wikipedia, which would be the depth of field of a camera lens. And this is the distance from the nearest object plane in focus to that of the farthest plane that is also in focus. And you can see here, you can see about 3 lines of text in this document in focus, and then as you move out of the depth of field, you can see that the image gets blurry. The image on the right is a representation of the depth of field for microscope lenses. And in the blue cone, you see what would be the depth of field for a low magnification, low numerical aperture lens, which is relatively large. And then as you go up to higher resolution, higher numerical aperture lenses, the depth of field is smaller. And we'll talk a bit more about numerical aperture shortly. So the depth of field along the z-axis of a lens can be seen here. This is an image set of a point source. So in the middle image here, the point source is in focus. And then as you go above and below the plane of focus, the image goes out of focus. And you can see here a diffraction pattern, which I'll also introduce a little bit more about that after. And this image on the right shows a view of the depth of field of a lens, where you can see the bright focus in the middle, and then things are out of focus as you move away from the focal plane. Field curvature is another aspect of lenses. So lenses themselves have curved surfaces. So the image plane is actually not flat, but a curved surface. So light that's focused through the center of the lens will focus to a different plane than light that's focused from the edge of the lens. And this is a problem if you're trying to look at a relatively reasonable field of view of a sample, in that the center of the image will be in focus and the edges will be out of focus. So the optic companies have developed optics that are added to the lens to create what are called plan lenses or plan-apo lenses. And this word plan basically means that the lens is corrected for field curvature. So this example here shows an achromatic lens and a plan-achromatic lens. And basically what's done is optical elements are added to the lens in order to correct for this focal plane being curved and making the focal plane an actual plane over fairly large distances, like 18 to 25 millimeters. And pretty much with modern microscopes, there's not many applications where you wouldn't want to have a plane lens. So I would recommend to always get a plan achromat and not an achromat lens. The lenses also have mounting threads, which can have different sizes. And traditionally, the mounting thread was the Royal Microscopical Society standard, or RMS standard, of 20.32 millimeters. And this is not used commonly now. More recently, lenses are 32 millimeters, but lenses can also be found that are 25 millimeters. And you can also buy simple adapters where if you have a system which has a 25 millimeter lens and you need, a system with a 32 millimeter opening and you have a 25 millimeter lens, you can buy one of these adapters to use older lenses on the 32 millimeter thread. And objective lenses are still made by hand, so it's my understanding the 32 millimeter mounting threads makes a larger lens, which gives the optic companies more room to work with to make specialized lenses. So numerical aperture is probably the most important parameter about a lens, and this is the range of angles over which the lens can accept or emit light, or the ability of the lens to focus the light or collect light. And this usually scales with magnification, so as you go to higher magnification, the numerical aperture tends to be higher, and as you remember, the working distance goes down. The numerical aperture is dependent on two properties, the refractive index of the medium and then the angle of the aperture. So it's actually the half angle that's in the numerical aperture formula. So one important aspect of lenses which is related to the numerical aperture is the brightness. And as numerical aperture increases, these are images taken with 3 different 20x lenses, and you can see going from numerical aperture of 0.4 to 0.75 how much brighter the image is with the high numerical aperture. And this is a really strong dependence because it's numerical aperture to the 4th power. The numerical aperture comes into play both with focusing the light on the sample and with collecting the fluorescence emission. You'll also notice that the brightness scales inversely proportional to magnification squared, and we'll come back to that later, but that's really important in choosing the right lens for sensitivity. So I'll move now, those are some of the basic features of lenses, and I'm going to move now to more specifics of applications. So if your application really requires the highest resolution in XY, what type of things do you need to think about? So I need to introduce a couple of terms. So diffraction is the most common aspect of a microscope lens, and it's what creates contrast in the image, but it's also what limits resolution. So diffraction is the bending of light as it passes a corner, an edge, or a small opening that's about the same size or smaller than the wavelength of light. And this is just a representation of diffraction through an aperture from Wikipedia. And what you see is in the middle here you have non-diffracted light. So this light's going to go straight through the slit, and it can then go onto a detector, and you would see a bright spot. You can also have constructive and destructive interference. So in areas where the light waves combine, so the light bends by diffraction, and some of those light waves will combine, you get constructive interference and you get a bright spot on the diffraction pattern that's away from the non-diffracted light. And you see this is symmetric on either side of the slit. You can also have dark regions where the light waves that are being diffracted interfere destructively, and these are the dark areas between these bright spots. So if we look at a point source in a microscope, then the light coming from this point source will undergo diffraction and will bend. And as a result, you get spreading out of the light. So the point source actually looks much larger in the image than the object actually is. And then you get these diffraction rings. So this is the same as what I showed you with the slit, but in this case you have a ring around the object. And this first ring is called the first order diffraction, the second ring is the second order diffraction, and the third ring is the third order diffraction. So most of the light is being directed straight into the sensor, and that's your light that's not diffracted. And then you can see the first, second, and third order diffraction, the rings get dimmer as you move away from the object. And an important property of diffraction is that lower wavelength light, like blue light, diffracts less than longer wavelength light, such as red light. So if you took the same object of the same size, but that object was red, then that object would actually appear larger in the image because the red light undergoes more diffraction, it bends more, and these diffraction rings are further away from the point source, and the point source itself also looks larger. So this is one property that affects the resolution of the microscope. This diffraction pattern is called the point spread function, so it's the way that the light from a point is spread as it goes through the optics of the microscope. And it's also called the Airy disk after Sir Airy, who was an English mathematician and astronomer who first described this diffraction pattern and called it the Airy disk. So if we go back to the microscope now and we have a specimen, say for example, a specimen that has a lot of order to it, so this is a pattern of lines here, then in at the back of the objectives you can actually see the diffraction pattern from that specimen. And in the first image here, this would be a low resolution, low numerical aperture lens. You can see the diffraction pattern, and then in the center you're seeing the slit or the aperture. And you can also see how the light is spread out. The blue light doesn't diffract as much as the red. In this middle example, you have a higher resolution, higher numerical aperture lens, and you can actually see the first and second order diffraction. And then in the highest resolution lens, you can see also the third order diffraction. And the important thing here is that it's the smallest features in the sample that cause the most diffraction. So these first, second, third order diffraction are corresponding to finer and finer details in the sample. So this higher resolution lens is higher resolution because it's collecting information from the smallest features in the sample. So if we actually want to define what the resolution of the instrument is, then we can use what's called the Rayleigh criterion. And this is the criteria for resolving two objects. And the definition of this is that the center of the point spread function for the first object, so say we take this object here is our first object, then the center of that object cannot be any closer to the other object than the first minimum in the diffraction pattern from the second object. So you can see that in this case we can easily resolve these 2 points and that the Rayleigh criterion is satisfied, but if these 2 points were closer together it would start to just look like one point. And this is just another representation of the same information, looking at a cross-section through this peak. So you can see the direct light that's not diffracted from the point source, and then the first, second, and third order diffraction bands. And you can see as these two objects move closer together, those diffraction bands start to overlap, and we really can't go any closer than that first minimum of the second object in order to resolve the two objects. So from a practical point of view, we want to say, okay, well, what is that number? What's that distance that I can resolve? And there's many, many definitions of resolution out there. They take into account different things such as the excitation light, the emission light, and so on. But the probably most frequently used and straightforward representation is this equation here, where the resolution is equal to 0.6 times the wavelength of light divided by the numerical aperture. And as you remember, the numerical aperture is related to the refractive index of the medium and the half angle of the aperture. So in this case, that angle would be 7 degrees, 20 degrees, and 60 degrees as we go to higher numerical aperture. So we can calculate the resolution of a lens for a certain color of light just by knowing the wavelength of the light and the numerical aperture. And a very important point here is that this does not depend on magnification. So when choosing a lens, magnification is not one of the most important parameters, although it seems like it should be. It's actually not playing into your resolution at all. So how can we increase resolution? If we want to use lower wavelength light, we could. So we could use this parameter here in the numerator, and we could move to, say, blue light. The problem with blue light is that blue dyes are not typically very stable or very efficient fluorophores, and we also end up with some photobleaching and phototoxicity. If we're working with live samples, phototoxicity can be an issue, and even with fixed samples, if we want to do imaging at high resolution or doing three-dimensional reconstructions, then the photobleaching of the fluorophores can be an issue. So this is possible, but it's not normally the first choice for increasing resolution. A better option is to increase the numerical aperture. So use a lens with higher numerical aperture, and you can use higher refractive index media. So oil lenses have higher resolution than water lenses, and water lenses have higher resolution than air lenses. And I'll talk a little bit more about that, why that is on the next slide. Maybe 2 slides. So the theoretical resolution can be calculated as shown here. So you can see the different magnifications, different numerical apertures, and then the theoretical resolution based on this equation. And this is for 550 nanometer light. So this would be something like green fluorescent protein or Alexa Fluor 488. And you can see here for 40x and 60x, we have the same numerical aperture. So those two lenses have the same resolution. And the same is true for 60x and 100x, where we have 1.4 NA. They have the same resolution. So one other term we have to understand in order to understand how the resolution can be improved using different refractive index media is the property of refraction. So refraction is the bending of light because light changes in speed as it goes from one material to another. And refraction occurs if the light is going between those two materials at an angle. So you can see that here in this image where we have a straw going into the water, and it actually looks like the straw is broken and that the image of the straw is over here. And this is due to refraction as the straw enters at an angle from the air to the water. You also might, if anybody has a fish tank, if you're ever putting your hand in the fish tank to move something around, it always seems like it's in the wrong place, and that's because of the refraction between the air and water interface in the tank. So refraction also occurs in the microscope, and we have the bending of the light when it goes between materials of different refractive index. So if we take this case on the left here with an air lens, we're going from, if light's coming from the sample, it's going from glass to air and then back to glass on the objective lens. And what happens is when that light passes from the cover glass to the air, we have refraction because we're going at an angle from material of one refractive index to a material of another refractive index. And you can see that the light bends, and the bending is proportional to the angle. So as we go at higher and higher angles, you can see there's more and more bending. And there's a point where the light bends so much that it's not collected by the lens. And there's even a point where if the light's coming out at a high enough angle, it will actually reflect off the surface between the cover glass and the air, and it will reflect back toward the specimen and not be collected at all. So the air lens can only collect, even though it could have a high numerical aperture, it can only collect the light that is not refracted or reflected outside of the lens. If we look at the case of an oil immersion lens, then glass has a refractive index of about 1.51. And if the immersion oil has a similar refractive index and the cover glass has a similar refractive index, then we no longer have that refractive index mismatch here, and so there's no refraction. So the light coming from the sample does not bend at the cover glass oil interface, and you're able to collect light, more light, and also the light that's highly coming in at a high angle. And if you remember when we talked about diffraction, it's this light at the high angle that's coming from the very small features in the sample. Those small features are causing a lot of diffraction, so the light is coming at a very high angle, and this higher numerical aperture immersion lens is able to collect that light. So that will give you more resolution. So if we think back to that diagram I also showed, it's these high numerical aperture lenses, which would be also can be water or oil immersion, that will be able to collect this highly diffracted light, this say third order diffracted light, and this is coming from the small features in the sample and giving us better resolution. So just to be clear, you don't always necessarily want to get the highest numerical aperture lens. There are some disadvantages. They tend to be higher magnification, so the field of view can be smaller. So if you want to do statistics, you have to look at more regions of interest. If you're imaging tissue, you may need to look at more areas. Immersion media can be messy and can damage lenses and microscopes, particularly on inverted microscopes. And if you have a large sample and you want to tile, usually the immersion media won't move to a large distance with automated tiling. And if you wanted to do, like, say, an 8-well plate and do 8 experiments, you would have to move manually between wells in order to have enough immersion media for that to work. They also tend to have a small working distance, so if you have a fairly thick sample, you might not be able to image through the whole sample. And a small depth of field. This could be an advantage or a disadvantage depending on your application, and they tend to be expensive. So although they're the best, high-NA lenses are the best for the optimal resolution, you should always be sure for your application that you really need that level of resolution. So what level of resolution do you need? So Nyquist Shannon came up with a sampling theorem to answer just that question. And the original work was actually done with the telegraph. And the question was, how much do I need to sample this sound so that the person on the other side of the telegraph can understand the transmission that I'm sending? And their theory determined that the signal must be sampled 2.3 times the minimum frequency of the sound in order for it to be recreated and properly understood. So this same principle can apply to microscope images. As a general rule of thumb, we tend to use an estimate of 3 times the size so that we're a little bit higher than we need to be, but it's a nice round number and easy to work with to do the math, even in your head if you like. So you take basically the minimum feature that you're interested in and divide that by 3, and that's the size of the pixel that you should have in your image. So for example, if I'm counting cells and the cells are 20 micrometers in diameter, I don't really need a really high resolution lens. I just need to be able to say this is one cell, this is another cell. So my pixels could be up to say 6.67 microns, and a low numerical aperture affordable lens would be just fine. And you can see from this image here, we can easily count the nuclei of these different cells. However, if you wanted to look at something smaller, so say for instance you wanted to look at focal adhesions and count the number of focal adhesions in a cell. This example here shows a single cell, and that's Paxillin GFP fluorescent protein. Then we would need to be more like 0.167 microns per pixel in order to count these adhesions. And you can see if the pixels are only 0.4 micron, that the image is very blurry and you wouldn't be able to count those adhesions. So it really depends, the sampling depends on the application you have. So choosing a lens for a camera-based microscope is a little bit different than choosing a lens for a laser scanning confocal. So for camera-based microscopes, this would include wide-field microscopes, spinning disc, even super-resolution microscopes tend to use cameras. You have a fixed pixel array. So there's a chip in the camera that has a fixed array of sensors, and those are your pixels basically. And the magnification you use changes the pixel size. So you may need higher magnification to get Nyquist Shannon sampling on your camera. And it's important to note that different cameras have different pixel sizes. So in choosing a camera for a wide field system, this would be something you might want to consider. So this example is using a fairly modern CCD camera that has very small pixels at 4.5 micrometers. And if you want to calculate the pixel size in your image, you basically take the physical pixel size on the camera and divide by the magnification of your lens. So in this case, the pixel size would be 72 nanometers. If we look at the same camera, but we have a 100x magnification lens, then the pixels would be 45 nanometers. So you can see from the schematic here that we have a lot more data points with the 100x lens than we do with the 63x lens. However, if you remember, we had mentioned brightness earlier, and brightness is inversely related to magnification squared. So this is an image taken with the 63x lens. This is focal adhesions and actin filaments. And this is the same region of the same sample, but with the 100x lens. And this is zoomed in more because your field of view is going to be smaller. The camera chip size doesn't change, so if you're magnifying more, then you're looking at a smaller region of the sample. And the 63x lens is actually 2.5 times brighter. So you can see the image is quite a bit brighter. If we zoom in a little bit to the same region of interest with the 63 versus the 100x lens, you can see if we increase the brightness artificially on the computer with the 100x lens, you can see that the sample looks fairly similar between the two. And the 100x is going to have smaller pixels, but you might be able to see that the images are actually quite a bit noisier in the 100x example because the signal is lower. So if we use a pseudocolor lookup table here, you can see the noise a little bit better, I think, here in the 100x lens. And we're going to zoom into this region of the cell and look at these two focal adhesion structures. And on the right here is a graph, which is the intensity profile along this red line for the two lenses. So the black shows the 63x lens, and the red shows the 100x lens. And what you can notice here is that for the 100x lens, we do have better resolution. So it seems that we have sharper contrast between these two adhesions. But you'll also notice that there's more noise in the signal for the 100x, and that the 63x lens, even though it has fewer data points, the precision of each intensity of measurement is better. And these curves were generated by using a 5-pixel average. So you look at 5 pixels along this line and average them. So if you looked at a single line, the noise would actually be quite a bit higher in the 100x. So basically the 63x has better signal to noise, even though the 100x has better resolution. And our resolution is also related to our signal to noise. So in this case, even though the 100x has higher pixel size, I think that the 63x is still giving overall a better quality image. This is also a camera that has very small pixels at 4.5 micrometer. So this comparison could be done on a different camera, and it may be that the 100x lens would be required. So it's important for the confocal laser scanning microscope that we realize things are a bit different. So on the laser scanning confocal, magnification doesn't matter. The number of pixels in the image is set in the software, so you can choose 512 by 512 or 1024 by 1024 for the same physical region of your sample. And you can use the zoom setting as well to look at a smaller region with the same number of pixels to basically set your pixel size to whatever value you need within quite a large range. And the pixel size is basically determined by how far the laser moves and how often the fluorescence signal is measured. So if you're at zoom 1, the laser beam is going to sit in this location and take one data point. And then as it moves, another data point will be collected here and here. Whereas if we're at zoom 6, the laser beam will be here and take a data point, and then in the next location take a data point. And so it's going to move less distance in order to collect more data points. And this you can play around with scan speed and zoom and so on, and really fine-tune the pixel dwell time and the pixel size for your images. Now the danger with having all that flexibility is what's called oversampling, where you may zoom in a lot to think you're going to get the best resolution image possible. But you can see from these three images here of actin filaments that going from zoom 1 to zoom 6 doesn't really change the physical image very much. And the zoom 6 is going to be a much larger image file, and not a lot of information will be added. So you really want to use the Nyquist-Shannon theory to find the optimal pixel size to minimize your file size, but get the best resolution possible. There is a couple of exceptions, like deconvolution and correlation microscopy, where you may want to oversample a bit in order to get the best data out of the analysis algorithms for these techniques. So if you remember now, we come back to brightness. If we take the 63x lens at 3.2x zoom, our total magnification is 200x. If we take a 100x lens at 2x zoom, our total magnification is also 200x. But the brightness is going to be 2.5 times higher with the 63x lens. So these are images showing the same region of the same sample, and you can see that the 63x image is quite a bit brighter. So if I change the contrast, so the 100x and 63x lenses have the same contrast, it's pretty hard to see the difference between these two images. They look quite similar. The pixel size is the same, and the image looks quite similar. But what you may notice is that the 100x lens again is a little bit noisier because the signal is lower, so the signal-to-noise ratio is going to not be as good. So if we do a similar exercise as we did for the wide field system, if we take the intensity along this line across these two adhesions, in the top graph you see that the 63x lens is a lot brighter, so you can see the peaks are much higher. And if we normalize those two curves, you can see that the data is quite similar. The pixel size is the same, so it's not like the wide field case where the 100x lens has more data points. And you can clearly see here that the 100x lens data is much noisier. This again is an average of 5 pixels across the line, but photomultiplier tubes are quite a bit noisier than cameras, so the data will be quite a bit noisier on the 100x. So for laser scanning confocal microscopes, it's really important not to purchase two lenses with the same numerical aperture and immersion media, but different magnifications. You're not gaining anything from those very expensive optics when you can just take a 60x or 63x lens and add 1.6 zoom and get to the same resolution. So what about sensitivity and speed? So I have a really dim sample or a really light sensitive sample, or I have something I want to watch that's occurring at a very rapid rate. The sensitivity will depend on the detector, so the camera or the photomultiplier tube. But from the objective lens point of view, you want to choose the lowest magnification possible, the highest numerical aperture possible, and you also want to check the transmission of the objective lens. So I'll show on the next slide an example of curves, but some lenses transmit different wavelengths than others, and this depends on the type of glass used in the optics. For speed, again, it's going to depend on your detector and the software interface. From the perspective of the objective, you can choose minimal pixel size using your Nyquist-Shannon sampling, and you can also choose fields of view or regions of interest. So in this case here, if we chose this region of interest and imaged it with the same resolution on a confocal laser scanning microscope, for instance, then this would be 4 times faster to image. Even on a camera-based system, you have to read out all the pixels, so if you have a smaller region of interest, you should also be able to gain some time. I also wanted to mention this 20x 0.8 NA lens, or some of the manufacturers have 20x 0.75 NA lenses. This is a really great lens to add to any microscope. You can see here with this image that you can see the actin filaments and the focal adhesions quite well, even with the 20x lens, because the numerical aperture is pretty high. And then because this is an air lens, you can use it for tiling to look at larger areas of your sample, and you can also use it for multi-point experiments. So you could use an 8-well dish and set up the software with a motorized stage to look at 8 different samples and really streamline your experiments on fixed or live samples. this is an objective lens transmission curve for two different lenses. And you can see in the visible range, they're both quite transmissive, up to almost 100% transmission in the visible ranges. But you see out here past 800 nanometers in the infrared range that the 20x.8 lens actually loses a lot of transmission in the infrared. So if you have an application where you're doing intravital imaging on a multiphoton microscope, you might be better off with the lower NA lens because it's going to detect more light. So the microscope companies either put these curves on their website, or if you're buying a lens, you can ask them to supply that information to make sure it's going to meet the needs of your application. So we also have resolution in Z. So if we're looking at a thick sample and doing a Z stack, what do we need to worry about as far as the objective lens? So the main issue looking into a sample is spherical aberrations. So because lenses are curved surfaces and we're going from glass to air, you see aberrations as you switch from the glass media into the air. You see refraction occurring. And this refraction is going to be dependent of the angle of the lens. So at the center of the lens, the light goes straight through, but at the edges you see quite a bit of refraction. And what this does is it basically gives you different focal points along the optical axis. So this can be corrected for using different types of lenses. So this is an example with an aspheric lens where the backside of the lens is flat, so you're not seeing the refraction occurring, and you get a much tighter focus. And in the microscope image, if you're doing a section through a sample, the spherical aberrations appear as a blurriness. And you can see in this aspheric lens that the image is much less blurry. One of the other causes of spherical aberrations is cover slip thickness. So the microscope lenses are almost always corrected for 0.17 millimeter or 170 micron thick cover slips, and this corresponds to number 1.5 glass if you're buying cover slips. If the cover slips are too thick or too thin, then the resolution is lost because you get spherical aberrations because the corrective optics in the lens is not expecting that layer of glass to be thinner or thicker than 170 microns. And the aberrations are worse as you go deeper into the sample. So this example here is just showing number 1.5 and a number 1 cover slip, and you should be able to see here that the number 1 cover slip image is quite a bit blurrier. And if we focus just on the nuclear staining, you can see quite clearly that the resolution is not as good with the number 1 cover slip. And this is a pretty flat sample. These are cultured cells that are probably only about 10 or 20 microns thick. So you can imagine if you had a tissue section and you were going further in that this effect will get worse as you go deeper. So you can minimize index of refraction mismatches, which will minimize spherical aberrations, by using oil immersion with fixed samples and mounting media that has the same refractive index as the oil. And you can also use water immersion lenses with aqueous samples. But here it's really important to set the correction collar correctly, and I'll show you a slide about that after. And in general, the refractive index of glass cover slips is about 1.52. So this is an example which shows different refractive index oil, and you can see in the center panel when the oil is best matched to the glass cover slip, we get the crispest image and the least blur, and especially along the z-axis when we have the oil matched. So for multicolor imaging, the major aberration we have to worry about there is due to dispersion of light. So dispersion is the wavelength-dependent refraction of light when it passes from one material to another at an angle. So it's really refraction, but the amount of refraction depends on color, and that's where you get the term dispersion. So if we have white light going into a prism, as it goes from the air to the glass, we get bending of the light, and then as it goes from the glass back out to the air, we get bending of the light again. And that's how a prism can basically separate white light into its colors. The red light will only undergo a little bit of refraction, and the blue or purple light will undergo a lot of diffraction, and we get this separation. So in the microscope, the same thing happens at a microscope lens. The refraction is different for the different colors, so the red refracts the least, so it's going to focus at the furthest focal point, whereas the blue undergoes more refraction and will focus behind, and then the green light is somewhere in between. So we have a different focal plane for the different colors. So the lens manufacturers can use optics again, different types of lenses. So achromatic doublet lenses, for instance, will correct blue and red light, and the blue and red light are brought to the same focal plane, but the green light is still in a different focal plane. And they do this by using different shapes of lenses and different types of glass to cause negative and positive dispersion to cancel out and bring the light to the same focal plane. So if you look at an achromat lens, it corrects for achromatic corrects for blue and red, but apochromatic lenses correct for blue, green, and red. And they basically have more optics again, using different lens shapes and different types of glass to bring the light together in the same focal plane. These lenses are more complex and they have more elements, so they tend to be more expensive. And they often have less light transmission as well because you have more optical surfaces that the light can reflect off of. So how does this look in the microscope? The chromatic corrections are really important if you're doing multicolor or colocalization type analysis. If you have a poorly corrected lens, you can see this is a multi-colored fluorescent bead, and you can see the green and red are focused down here and the blue is way up here. Whereas in a well-corrected plan apo lens, you can see that all the focal planes are matching up. So this is important for multicolor applications. If you don't have a lens that meets these criteria, what you can do is image these multicolor beads and then digitally correct the images after you collect the data sets. In a biological sample, this would be an example of poor color correction where it looks like there's independent green and red signal and some area of yellow, whereas when you have good correction, you would find that these structures are actually colocalized. So just to wrap up, I'll just mention a few specialized objective lenses. You could probably give a whole seminar on specialized lenses, but I just wanted to mention a few. Long working distance lenses are usually used to image through tissue culture plates, to image large sections of tissue or maybe small organisms. They don't have immersion media because they have to be quite far away from the sample. And I always am intrigued by the crazy number of acronyms out there. So I think probably LWD is the most common for long working distance, but there's also extra long, ultra long, super long, and it seems the different manufacturers all have their own abbreviations, so you may have to do some research to look them up. Phase contrast lenses have an etched phase ring at the back of the objective in this lens element here. And these are good for wide field applications, but this phase ring will actually reduce your fluorescence sensitivity a little bit. There's water dipping lenses, and these have a Teflon coat. They don't go through a cover glass, but the lens is dipped right into the media. So these are used on upright microscopes, typically with biological samples in an aqueous environment. And the important thing with these is to carefully clean them to avoid buildup of salt and protein on the lenses after use. So they need to be rinsed really well with water after use. You can also get specialized lenses for, say, UV or IR transmission, like the 20x lens I showed you earlier. And these are really important if you're working in the 200 to 400 nanometer UV range or out past 700 nanometers. And the last one I just wanted to bring attention to is the water immersion lenses. So these can be used if you're using an inverted microscope and you have a cover slip and then your sample is in an aqueous media. So often for live cell applications, for instance. And you minimize spherical aberration because of the index matching. But the issue is that these lenses almost always have a correction collar to correct for the thickness of the glass between the sample, the cover slip basically between the sample and the objective. And if the collar is not properly adjusted, then the resolution can be really, really poor. So we did an international study which was published in 2013, and we found about 45% of the data that was submitted for resolution analysis probably had the correction collar set incorrectly. So this is an example of a point source shown in the water lens that is properly adjusted, and then on the right is one that is not properly adjusted. And you can see, especially in Z, the resolution is completely lost here. The point spread function is about 2 microns high, whereas here it's about a half a micron. So if that's the case, that the lens is not properly adjusted, it would probably be better to just use the oil lens and have some small spherical aberrations due to the index mismatch, rather than having these huge aberrations if the collar is not correctly adjusted. So this is just a summary of the different types of lenses and what they're corrected for. As I said earlier, I think it would be best to always get a plan objective, so it's corrected for field curvature. And then the achromat is corrected for a few colors for spherical and chromatic aberrations. The fluorites are corrected for more, and then the top end lenses, or the apochromats, are corrected for multiple colors for both spherical and chromatic aberrations. And the price tends to go with those corrections. So the more optical elements and the more corrections, the more expensive the lens. So if you're setting up a microscope and need to get lenses, this would be a recommended set. You need a 10x.3 for just general use, long working distance, relatively low cost. I really recommend this 20x.8 or 20x.75 type lens. Has excellent resolution, great for tiling and multi-point, and has a moderate cost. It does have a lower working distance though, so depending on your application, it may not be ideal. And then we have the 63x1.4 NA oil immersion for general purpose high resolution, has good brightness and higher cost, but as a workhorse lens, it's worth the investment. If you are on a budget and you're not doing large samples or multi-point, then a 20x.5 is also a great general use lens, and it will have a bit longer working distance, which can be helpful and a lower cost. If working on yeast or bacteria on a wide field microscope, then that's those are two applications, I guess, where the 100x lens can be really helpful to get those smaller pixels. For larger samples, you may want to get a 40x1.4 oil instead of the 63. Again, this will have similar it should have the same resolution and even higher brightness than the 63. And if you're working with thick samples in aqueous media, then the 40x1.0 water is a good lens, but you need to make sure you set that correction collar properly. For more information, I've put links to the 4 major microscope manufacturers' websites for objectives, so you can get more information there. And I'd like to thank you and I wish you happy imaging.